Hello, this is the next video in a playlist that I'm calling Hypothesis Testing. And here this is a follow-up video to my previous video. And the previous video was called Simple versus Simple Testing for the Gamma and Poisson distributions. And so we're going to do some simulations in those regards. First of all, I like to remove all the objects the in the memory of R. And here we're going to look at the gamma distribution. We're going to assume that alpha is known and is equal to the value of 2. We're going to take a sample size of 22. The null hypothesis is that the beta parameter is 5. The alternative hypothesis is that beta is 7. So beta 0 is 5, beta 1 is 7. And I just want to plot these distributions to show you what's going on graphically. And here they are. So under the null hypothesis, this would be the distribution we're looking at. And it's specifically the sum of our data. So it's the sum of the x's is the distribution that we're looking at. And again, it's a gamma distribution. And this would be it. And this point right here is the critical region. So the area in the tail under the distribution, assuming the null is true, is 5%. Now, if the alternative is true, then this red curve indicates the distribution under that, when the alternative is true. And the power would be the probability of rejecting when the null hypothesis, when the alternative is true. So it'd be the area under that curve. So graphically, that's kind of what we're going to be simulating here. Now let's look at our simulation. We're going to use the same assumptions, and that is the null hypothesis beta is 5, the alternative is beta 7, alpha is known as 2. We're going to do 1 million replications. CR here, sample size 22. CR stands for the critical region. So we want the 5% of the tail under the null hypothesis. So we're assuming that beta 0 is true. And since Q gamma calculates the area left, the cumulative, we want it 95%, which means the tail area is 1%. Now what's kind of interesting, or at least maybe I think it is I put the random samples in a matrix. So the number of columns is n, so there's 22 columns, and the number of rows is the reps, so there's 1 million. But we only want the sums of our sample, so I take row sum, so it creates a vector of size 1 by 1 million. And then we check to see each of those above or below the critical region. And then we table them. And that's how we're going to calculate the size of the test. And then we're going to repeat it, but we're going to assume that the alternative is true. And that's what we're doing here. And now this machine that I'm running it on is a Linux-based machine that's actually not very fast. So it just finished, and the size is 0.05, which, alpha 0.05, and that's what we were aiming for. And the power is 74%. And let's do this again, but increase the sample size to 33. So here, we're creating that matrix. This is probably not very efficient to create a 1 million by 33 matrix and then take the row sums of each of those. There's probably a more efficient way, but this works and it's easy for me to understand, and so I created it. So again, the size of the test is right hovering around 0.05. The power is 87% instead of 74%, so we went up by 12% or 13%. And that's how you'd conduct these simulations using the gamma distribution. Now let's move to the Poisson distribution, and we're going to let me first tell you that under the null hypothesis, we're going to assume that lambda is 1. The alternative is that lambda is 1.5. We're going to initially assume a sample size of 33, or at least for this graphical representation. So I just want to plot the Poisson distribution and the critical region for this test. So the null hypothesis is that lambda is 1. The alternative is lambda 1.5. We're going to take a sample size of 33, and we want as close as possible of a 0.05 test. And so when we run that, we get this. Now, since it's a Poisson, the mass is on a point, so it's actually those vertical lines. But I put the continuous line above it so you could see it a little bit better. So the null hypothesis, if the null hypothesis is true, this is the distribution that we get from the sum of our sample, the sum of the x's. And this dot down here, hopefully you can see that. That point makes it in the area in the tail such that it's 0.05 or at most 0.05. And the red is when the alternative is true. This would be the distribution under the alternative. And then of course the power is you add up the heights of those bars, and that would be power. So that's kind of visually what's going on. So let's do the simulation. We're going to do the simulation with the same assumptions. The null hypothesis is that lambda is 1, the alternative is 1.5. We're going to do 2 million replications because somehow this is faster in simulating Poissons than the others. Since it's discrete, we're going to do both a randomized test and a non-randomized test. In the randomized test, if you watch the earlier videos in this playlist, hypothesis test, it talks about what a randomized test is. So let's do a sample size of 20. And I use the same approach where I create a matrix and I put the random samples in there. I do a row sum because that's really all I need. And then I look to see whether it's above or below the critical region. But I also, and maybe I should point this out, I have to add another one, is if it equals that point and and then we randomly reject based upon gamma. And that's what those little if statements in there are doing. So let's run this and see what we get. So it's currently running. So we're doing 2 million reps. So it takes a second or two for each little time it runs and then calculates. The randomized part of this is much slower than the non-randomized test. So the randomized test, where we try to shoot for an exact 0.05 size or significance level, and it's really close. The non-randomized test is, the best we can do is an alpha of, and not go over 0.05, is 0.034. And theoretically, we should hit, that's the theoretical, and then simulation, we were really close to that. The power for the random test theory says we should get about 65.7%, and the simulation was very close. The non-randomized test, which should be less powerful, is indeed less powerful. So the theoretical we should get, around 60%, and we got that in our simulations. So let's increase the sample size from 20 or 22 or whatever it was to 33 and see if it increases the power from 65 and 60% to something more. So let's do that. So I just ran that, and it's crunching those numbers. That's what it paused when it created that big matrix, 2 million by 33 matrix, and then took the row sums. And now it's doing it again under the alternative hypothesis, and then it just boom. So notice it got stuck on the randomized test, and when the non-randomized, it just went right through. So theoretical, remember this is the data is discrete. So the randomized test theory said we want a 0.05, and the simulation was so close to that. Non-random, the alpha or the significance level is 0.038. The power went up from 65% and 60% to 83% and 80%. So it did increase power, as it should. And I'm just going to do one more where we do a sample size of 66 and look at the power. Now, in the comment section, the first comment, I'm going to copy and paste this code, And what's kind of interesting, I would love to put it in the description, but a lot of these symbols, YouTube doesn't let me copy and paste these symbols into the description. And I think I only get so many letters, so it's always too much. But I can post whatever I want in the comments section. So that's why I put it in the comment section. So now, so this is so the power went from 83 and 80 to 98 and 97. So we didn't increase power. The size of the test for the randomized test is as it should be, really close to 0.05, and the non-random test, the alpha level is 0.04. That was just the best we could do without going over 0.05. And here's the type 2 errors. Those start decreasing a lot, especially you can notice when the power is large. Okay, well, that's all I have for this video. Hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.